In this video, I'm going to talk about completing circuit problem calculations when you have multiple batteries in your circuit. So the two rules that we're going to use are Kirchhoff's laws. The first is the junction law, and the junction law is a conservation of current law. So it tells you that since we know that charges, electrons are not being created and they're not being destroyed, current is not being created and not being destroyed, then the total current going into a junction has to equal the total current coming out of the junction. You can't have more current going in than coming out because the current has to go somewhere. And those charges have to go somewhere. They have to be somewhere. So that's called conservation of current, the junction law. And we also have the loop law, which is conservation of energy law. And that tells us that the delta V, so the change in potential around an entire loop, is equal to 0 if you go in an entire loop. We know that the delta V of the whole loop is going to be the total delta V, and if we think about a particle traveling in an entire loop, it's going to start and end in the same place in the circuit, so its electric potential energy would be the same in the beginning and in the end, so the change in electric potential energy is 0. We also know that potential is equal to electric potential energy divided by charge. So if we divide that by charge, then we know 0 divided by the charge, we just get 0. So our delta V for any loop is 0, and that's conservation of energy. So let's talk about the steps for solving these problems. The first thing you're going to do is draw the circuit diagram. There may be some simple circuits that you can do without drawing a diagram, but these, it's really important to draw the diagram. It's going to be really hard to keep track of things if you haven't drawn your diagram. So make sure you draw your diagram. Next thing you're going to do is assign the direction of current in every branch of the circuit. It's okay if you're wrong on this. If you're wrong, then you're just going to get a negative number in your calculation, so just take a guess. Sometimes it's kind of hard to predict which way the current will go in a certain branch because of the multiple batteries. Then you're going to travel around a loop, so you need to draw this loop travel. And you've got to assign your arrows of travel to help you determine what to write your equations for your loop law. So when you're doing this, when you're traveling for your equations for your loop law, if you travel through a battery in the correct direction, current goes out of the positive side of the battery into the negative side, then your delta V is positive for that battery. If you travel the opposite direction, so if your loop travels backwards through a battery, then your delta V is negative because you started a higher potential and ended a lower potential as you go through the battery. For resistors, these can be kind of tricky. You should have 2 arrows for every resistor. One is your assigned current that you did in step 1, I think it was, or 2, step 2. Then the other one is your direction of travel arrow. If those arrows are the same direction, then you are going to have a decrease in potential when the current goes through the resistor. Those charges are losing energy as they go through the resistor. So you're going to have delta V be negative. So you're going to have negative IR when you write out your equation. If your assigned current is opposite of the direction of travel, then you know that your assigned current here, you're assuming that your current is going to be going from a higher potential to a lower potential. But when you're traveling through that for your energy statement, you're going from a lower potential to a higher potential. So you're going to have a positive delta V because you're traveling opposite of the direction of current. Okay, so we're going to give this a try. I'm going to do 3 examples. This is the first example, and it is the simplest. There are no branches, so when you don't have branches, you have a pretty simple situation. So the first thing I'm going to do is assign current. Now, what I always do is just find the biggest battery and assign the current coming out of the positive side of the biggest battery to start off with. This only has 1 branch, so it's only got 1 current statement. So I'm going to say that's my direction of current. And then I have to have a travel loop. So I'm going to travel in the same direction to make my math easier. and that will be my travel loop. So the travel loop isn't marked with an I, it's just marked with a loop arrow, usually on the inside, but it could be on the outside of your diagram too. And then we're going to write our equations. So we're doing the loop law, so we know that 0, our change in V is going to be 0. So 0 equals, when we go through my 9-volt battery, we add 9 volts of potential, so we have potential difference, so we have 9 volts there. Then we're going through the resistor, and the loop arrow and the current arrow are in the same direction. So we're going to subtract the potential difference between this side of the resistor and this side of the resistor. Now we know that delta V equals IR, so I'm just going to skip right over the IR, or the delta V part, and I'm going to put 40 ohms times the current. And then I get to the next battery, and this time I'm going backwards through the battery. I'm going from the higher potential side of the battery to the lower potential side of the battery. So I'm going to subtract 6 volts. Having this battery in the circuit is making it have less current. And I have less energy when I go from here to here. And then I go through the 20 volts or 20 ohm resistor, and once again my current, which is going around the loop like this, is in the same direction as my travel loop. So I'm going to subtract 20 ohms times the current. And now all I have to do is solve that. So I can see I have 9 divided by 9 minus 6, and then I can add my 40 plus 20 over, so I end up with 3 volts equals 60 ohms times I, and then I can isolate I, 3 volts over 60 ohms, and that gives me 0.05 amps. So that's a pretty simple one. Let's try a more challenging one. So in this circuit, I have multiple branches, and I have 2 batteries. So the first thing I'm going to do is assign my direction of current. So I'm going to call this right here I1, and this is the current in this whole branch here. Then the current has to split. Now I have to decide, I think it's probably going to be pushed this way, but it's hard because this 3-volt battery I know is going to push, push this way. So I'm pretty sure this is going to go this way. So let's just put I2 here, and then I3 here. So in our last problem, we didn't use the junction rule because there were no junctions. But now we're going to use the junction rule. And because of law of conservation of current, we know that I1 is equal to I2 plus I3. Because all the current going into this junction has to equal the current coming out of the junction. So that's our first equation. Then we're going to do our travel loops. And like I said, I usually like to come out of the positive side of the biggest battery. Now, but there's several different options for these loops. So I could make this little loop up here, I can make this little loop down here, and I can make this big loop, this entire big loop. So I'm going to choose, and it doesn't really matter, you'll get the same answer no matter what you do. So I'm going to choose that as loop 1, and then I'm going to choose this as loop 2. Okay, so now we're using the loop rule, and we're going to write our equations. So for the top loop, let me call this loop 1, or maybe loop A, since I have, and we'll call this loop B. Okay, so for loop A, we have the equation 7 volts, 0 equals 7 volts. And then it doesn't go through any resistors on this branch. So all you have is the 10 ohm resistor on this branch here, and I2 is the current that's going through that. And the loop and the current are going in the same direction. So you will have minus 10 ohms times I2. So there's one of our equations. We can also write an equation for loop B now. And loop B, I'll start at the battery, is 0 equals 3 volts, because we're going through the battery the normal way, so 3 volts. If we were to start here, we add 3 volts of potential difference. And then we're going here and we're going backwards through this one. So you can see that we're traveling through the resistor the opposite direction of the current. So we know that we're going from a lower potential to a higher potential since the current's going the opposite direction. So we're going to add 10 times I2. Then we come down here and we are going through the 20 ohm resistor, and we're going the same direction as current, so we know we're going from a higher potential to a lower potential, and it's I3 that's going through this one. So we will subtract 20 ohms times I3. Okay, so now we just have a system of equations to solve. We have 3 equations and 3 variables, I1, I2, I3, and 3 equations. And we're just gonna solve. So we're gonna start with this one because this is the only one that only has one variable. So we'll start with equation for loop A. And we know that 7 volts is equal to 10 ohms times I2. So I2 is equal to 7 volts over 10 ohms, which is going to give us 0.7 amps. Once I have that one, then I can, let me draw some arrows here so that you know what's what. So that's there. And then now I can use this equation since it has I2 in it and I know what I2 is, and then I3, that's the only one. I3 is the only variable that's unknown there. So we have, we'll just move the 3 volts over. Okay, so 3 volts is equal to, I'm actually moving this over and then subtracting that. So 20 ohms times I3 minus 10 ohms times I2, which is, I should have drawn that arrow a little bit differently, but 0.7 amps. And then we're solving for I3 here. So we get I3. So I'm going to subtract the 10 ohms times 0.7, which is 7 amps. And then I'm going to divide by 20. So, or 7 volts, sorry. So we have 3 volts. And then I'm going to add the 7 volts. And then I'm going to divide by the 20 amps. And so I get 1.2 amps. No, I looked at the wrong line in my calculations, sorry. It's like, that doesn't make sense. 10 divided by 20, it's not 1.2. 0.5 amps. So there's I3. So here's I2. Here's I3. And then from there, we can use the equation from our junction rule. And that equation is I1 equals I2 plus I3. So we just plug in I2, which is 0.7 amps, and I3, which is 0.5 amps, and we get 1.2 amps, which is the total current. There's my 1.2 amps. Okay, so that's a pretty typical problem that you would have to do with two batteries. I want to do one more example, and this time I want to show you what it looks like when you have a negative current. So when you have chosen the wrong direction for the current. So let's do this one more. This one has 3 batteries in it. We have a 10 volt, a 6 volt, and a 3 volt. They're all facing the same way. So my first step is to assign my currents. So I'm going to say that this one is I1. I'm going to say that I2 goes this way. And I'm going to say that I3 goes this way. Now, as you do enough of these, you'll kind of get the feeling for where the current's going to go. And I'm purposely doing some currents in the wrong direction so you can see what it looks like. It doesn't matter what you choose because you'll just get a negative current in your calculations, and then you just know it goes the opposite direction. Okay, so there's that. And then I'm going to also show you what it looks like to do one of your loops for your, like that outside loop. All right, so we can write our conservation, our loop law, or sorry, junction law or rule. I don't know what we should say. Some places call it a law, some places call it a rule. We have I1 equals I2. Oops, I did that wrong. I1 plus I3 equals I2 because they come together to get I2. So I1 plus I3 equals I2. And then we're going to do our loops. So I'm going to choose this as my first loop up here. So we'll say that's loop A. And then I'm going to do the next loop as this whole big outside loop. So I'm going to miss that middle branch, and I'm just going to do the outside loop. And that one is going to be B. Okay, so now we're going to use our loop law or rule. Doesn't really matter. And for A, we're going to have an equation. For B, we'll have an equation. Okay. So for A, when we follow our loop law, we start off with 0 potential. So you start at the negative side of the biggest battery is what I usually do. We go through this one, we add 10 volts. So we have 0 equals 10 volts. Then we go through this resistor. I'm traveling the same direction as the current. So we expect it to be going from higher potential to lower potential. So we're going to subtract 50 ohms times I1. Then we go here through this middle branch. So we're going backwards through the battery. We're going from the higher potential side to the lower potential side. So that means we're going to subtract 6 volts. And then we're going through this 100 ohm resistor again in the same direction as current, because current in this branch is going this way. So we're going from the higher potential side to the lower potential side. So we're going to subtract 100 ohms times I1. Ooh, I'm almost out of room here. Okay. So there's our first one. Then our second loop, loop B, we're going to go through the battery. So I start at the negative side of the biggest battery is usually what I like to do. It doesn't really matter where you start, but we add 10 volts. Then we're going the same direction as the current on the 50 ohm resistor, so from higher potential to lower potential. So we're subtracting 50 ohms times I1. Then we go down here, and this time we're going this way through this resistor, but the current's going the other way. So since the current's going the other way, it's going from higher potential to lower potential, and we're going, since we're traveling the opposite way, we're going from lower to higher. So we're going to add the 30 times I3. And then we're traveling backwards through the battery. So we have the positive side to the negative side. So we're going to subtract 3 volts. And then we are going through this last resistor, and we're going the same direction as the current. So that's the minus, maybe even less room on this one. Let me see if I can just move this over. Okay, so then we have minus 100 ohms times I1. All right, so now we have our 3 equations and our 3 unknowns, 1, 2, and 3. And there can be more than 3 unknowns. If we had more branches, you could have 4 or 5 or 6 or 8 unknowns, and you would have 8 equations. That's a little bit messy in the algebra, so I wouldn't expect to see much more than 3 different currents on your assessments, but I'm not saying it couldn't happen. Okay, so here we have 3 variables. Not going to use that one to solve. Here we only have 1. I1's the only one we don't have, so let's start there. And then here we have I1 and I3. So we'll use this to solve for I1. We'll plug it down here to solve for I3, and then we'll plug it up here to solve for I2. So if I get all of these, if I subtract the 6 volts from the 10, and then I add these 50 and 100 and then add them to the other side, I'm going to get 150 I1 is equal to 4 volts. Oh, and I forgot my little ohm. So I have I1 is equal to 4 volts over 150 ohms. And that gives me 0.027 amps. And then I can plug that in down here. So this is step 1 here. And then step 2 is to plug this in to these equations, to this equation here. And I have to isolate I3. So I think I'm going to do that first. Let me simplify this. So I get 0 equals 7 volts because I have the 10 minus the 3. And then I'm going to subtract the 150 I1. So I'm combining the negative 50 and the negative 100. And then I'm going to add 30 times I3. Being a little sloppy with my units here, sorry. Then I'm going to isolate I3 before I plug things in, just to make it a little easier. So 150 ohms times I1 minus 7 volts over 30 ohms. Okay, so now I can plug in I1. So I3 is equal to 150 times 0.27 amps minus 7 volts over 30 amps. So we get I3 is equal to negative 0.1 amps. So we got a negative number here. The negative number, what color haven't I used? I've used them all. So negative number means current goes in the opposite direction. So that would mean that I3 actually goes this way. I don't want to use, oh, green, I've used green. So this is the actual direction of I3. So just circle this in green so that you know it goes with that. Okay, so then our last step is to use my junction rule. I1 plus I3 equals I2. So all we have to do is say I2, step 3 here. So I2 is equal to I1, which was 0.027 amps, plus I3, which was negative 0.1 amps. So we can see already we're going to get a negative number, right? We get negative 0.073 amps. So once again, we have current 2 goes in the opposite direction. So this current right here is the actual direction of current of I2. All right, that is it.